Thank you, Professor Atre. My name is Virendra Sethi, and I'm here on behalf of Professor Suparna Mukherjee, head of our department, who is a little tied up with the PhD defense. So it's my pleasure and honor to introduce Professor Subhankar Karmakar. He joined our Environmental Science and Engineering department in December of 2007, and he holds a position of a professor here in our department since December of 2018. He's also an associate faculty member in the IDP in climate studies, as well as a Center for Urban Science and Engineering. Professor Karmakar obtained his PhD degree from IISc Bangalore, and then he worked as a postdoc fellow at the University of Western Ontario, Canada. He's been the recipient of the Voice Cast Fellowship from the Government of India, and which was utilized towards his research at Duke University, North Carolina. His primary interests are in the research areas of environmental systems analysis, uncertainty modeling, and risk vulnerability analysis to climate-induced natural hazards. With that, I now request Professor Karmakar to present his work on precipitation extremes and urban flood management. Thank you.
Yes, first of all, thank you very much, Professor Sethi. So I'll quickly share the screen. So I have today, the title of the presentation I kept as I have, written the research theme title, like Precipitation Extremes and Urban Flood Management. So in this particular work, talk, I would like to show you a few representative work which I have been doing since last 7 years on urban flood management at IIT Bombay. So most important slide is this. I would like to first convey my sincere gratitude to IRCC IIT Bombay for selecting or for identifying my research work for Research Publication Award 2019. I would like to thank my parent department, EACD, IDP Climate Studies, and Center for Urban Science and Engineering. Also, I would like to thank my funding agencies who have been funding many of my research projects, sponsored research projects. Also my collaborators, especially my friend, Professor Shubhimal Ghosh from Civil Engineering Department, and Professor Raghu Muktugudde, who is currently visiting faculty at IIT Bombay. So, of course, my students, actually, with whom I have been working since last 11, 12 years, and I have learned a lot from them. So thanks a lot to all of them. Yeah, sorry for the inconvenience. Here, all data sharing organizations like MMRDA, MCGM, because the work which I'm going to present now and which was the theme, research theme of for this particular hour. So it was very data intensive. I got collected many data from different civic bodies, and I'm grateful to them. I could not acknowledge each and individual people who involved in this work, who shared the data with me and my students. So then I would like to show you this particular slide where the 4 research projects I have listed. And here basically, since 2013, we have been working on different, mainly like the urban hotspots, which we have selected. For example, for Mumbai, for Chennai, for Jagat Singapore district, which is a very flood-prone, cyclone-prone area, like in Odisha. Also, we have been working at a national scale also, for entire India, we are developing hazard map and vulnerability map. And finally, our plan is to develop a very high resolution, risk map for entire India. So you can see that many co-PIs and many investigators were involved and who helped me to accomplish the goals whichever we have we had listed in these sponsored research projects. So I have started my journey to develop the flood risk map for different urban centers and also for entire India, almost 7 to 8 years back. So first, I saw this paper by Stephen Halligan in 2013, which was published in Nature Climate Change, and where he has performed a study over 136 cities across the globe. And he found, and his group found, that Chennai, Mumbai, Kolkata, and Surat among the top 12 global cities which are going to be affected due to intense urban flooding. So also in the same year, Jongpan 2013, he published another paper on nature climate change. And he has shown that not only the probability of occurrence of flood, we need to consider what is the demographic status. So for that, actually, like for that, like he has like specified that social vulnerability analysis or infrastructural vulnerability analysis, I mean, all components of vulnerability should also be performed. So like that means not only the probability of occurrence of any flood event, we need to consider what is the demographic status, like a couple of, like examples, for example, like population below 6 years, population above, like above 60 years, population like below poverty line, also number of households. All this information, if we can collect, or if we can somehow integrate with the chances or the like exceedance probability, then we'll get more useful information. So that's why, like, after Jonkman, so I thought like it is very important to include like flood vulnerability information along with the hazard information. So then in 2014, like AR5 report of IPCC came, and there also it was explicitly mentioned by Oppenheimer uh, in this AR5 report, where he has shown this schematic diagram, and he has mentioned that risk is a combination of three components, like vulnerability, hazard, and exposure, where he has mentioned that along with the hazard, which is, by definition, which is probabilistic information, along with that, some demographic information like vulnerability should also be included to generate the risk map. So you can see that it is basically, it is showing the intersection of three components like hazard, vulnerability, and exposure. And if you change the area under each of the components slightly, automatically the area under this spherical triangle of risk will also change. So in this way, if you can quantify the flood risk for each and every spatial location, and then you will be able to map, or you will be able to generate the flood risk map at a regional scale, or maybe at like at a country scale. So then the fourth point, which I found very interesting, and I found it is very challenging, and so that's why I wanted to start working in this area. So this is showing you a schematic diagram of the urban catchment, where you can see that the red color blocks are showing the building blocks. Urban catchment is always complex because runoff generation will be very very high compared to the rural catchment, because here the impervious layer will be more, and automatically the shape of the hydrograph, which is nothing but the time series of discharge, that will also change drastically. So in this particular urban catchment, if you see that there are river channels and also overland flow, which is basically the surface runoff, and also there could be like sewer flow. I mean, like stormwater drainage flow. It could be a combined sewer system also, where stormwater and the sewage can flow together. And so all these components we should consider uh, while modeling or while performing hydrodynamic modeling. But at the same time, the most challenging part is to consider all the interaction. For example, river overland flow interaction, like then sewer overland flow interaction, sewer river interaction. And of course, if it is a coastal city, then we should consider the tide river interaction also. So for example, like Mumbai or Chennai, it has like these are all coastal cities. And modeling this part, particularly, what would be the backwater flow and what would be the influence of high tide in the urban catchment, like quantifying that is always difficult. So these are the 4 points which gave me the impetus to work in this area, and I thought to pursue my research on particularly extreme rainfall like analysis, and also the flood risk mapping and flood forecasting. So lessons which I learned and the future needs that I wanted to show here, like the because future research aspirants, or like I thought that the talk is open for the students also. So that's why I wanted to share my the whatever experience I had, and I think in future we should be careful, and we should consider them as a potential research area, and we could bring the improvement in the flood modeling platform. So for example, first point is Saint-Venant equation, which is basically, people say it is basically combination of conservation of mass and also the like conservation of momentum. But I would say it is conservation of energy and also conservation of momentum. So this particular equation is very much useful, and oftentimes we use while doing hydrodynamic modeling. But a major assumption which we always impose, that the equation is applicable to mild slope and like mild to moderate slopes, but not for the steep slope. Then what will happen for the steep slope catchment? For example, Mumbai, in the upstream side of Mithi River, if you see, the slope is very steep. So that time, at that particular location, the Saint-Venant equation may not work. So some changes we need to bring, and we bought that for like on the Saint-Venant equation. Also, always in the past literature, they have shown that overland flow, which is typically a 2D like flow routing system, which is always like complicated. And past researchers, they brought many complexity on the overland like flow routing. But we found that kinematic wave like technique, which is very simple, which should be introduced, and also the application of kinematic wave routing technique should be more, so that you can deal with this overland flow routing in more easier manner. Also, absence of accurate river bathymetry, that means mainly like the underwater topography of the river channel. Even for the coastal cities, the underwater topography of the like of the sea is not very much available. So for that, and also it is very expensive. Sometimes it is very expensive. So we need to do
Last 2 minutes,
research.
Professor Karmakar.
Yes, sure. And also no provision for the like observed flood footprints that show the spatial pattern of areal extent and the flood depths at different intervals. Also 1D 2D flood modeling platform, actually this is very unstable model. So to increase the stability, we should have we should have more robust flood modeling platform. Even the flood forecasting system, which is basically most important input of flood forecasting system, is the forecasting of the precipitation. So numerical weather prediction model should be improved, and improved statistical and dynamical downscaling technique for extreme events. Also, we found that there should be, as the flood model may take huge amount of time to run, so that's why there should be a flood inundation library, which we should keep with us. And there should be a very good search algorithm through which you can find out the most appropriate flood inundation library for a given like return period or for a given input. So, and then also, like we found that for the data scarce situation, so there should be very efficient technique like should be followed for this, like through which you can find out some alternative of this man-made drainage network and the rainfall information. And finally, there should be like automated sensor-based devices. In Indian cities, the chances of vandalism is very high. So because of that, we should have proper protection to place the sensor in right places, and so that we can get the water level like inside the stormwater drains as well as the open channels. Also, socio-economic vulnerability map. These are usually indicator based. So many data, for example, migration data for Mumbai, it is not available. So these information should also be integrated. And finally, for general public, water professionals, and decision makers, this information should be disseminated through the web-based flood information system. So I'll just show you a few slides on the representative studies which I have done on Mithi River catchment. So here, actually, in this MOES project, we have developed the flood forecasting system, where we have included the numerical weather model WRF, and 6 to 36 hours lead time rainfall the forecast were used in the Mike flood platform, which is 1D 2D model, where we have considered the tidal influence like also. Here, the high resolution LiDAR data we could not use, but 2-meter resolution survey data we have used here. And finally, we could generate the maps. So parallel to this, we have generated the social vulnerability map for entire like Mumbai, which is showing basically mainly the social vulnerability map, and different techniques we have like followed to show that which method is the best. And very interesting result also we got for social vulnerability map. We have performed the complete flood risk mapping. Here you can see that the first time we have considered this bivariate risk map where vulnerability as well as like hazard, which is hazard is the probability of the occurrence of the event, and the vulnerability is the propensity of the damage. Both could be shown in this 3x3 matrix. So total 9 color codes which are showing different combination of the risk. And also, like, we have done the monitoring
So Karmakar, time is over. Please.
Sorry.
Can come to the last slide, please. I cannot take the questions also because
Yes,
you have eaten up the entire time now.
Sure. So I'll just show you the last, basically our plan. Like recently, we have published this tide equivalent rainfall, so a new metric, which is basically like quantifying that whether a particular region is storm tide dominated or extreme rainfall dominated. So here, this particular metric is very new and should be performed for other coastal catchments, so that this TRFQ values we should find out for entire coastal region of India. And interestingly, we found here that like Mithi River catchment, which is which is basically which is located in Mumbai, is basically storm tide dominated, and whereas like Chennai or the Greater Chennai Corporation and Jagat Singhapur area are they have the more fluvial impact or the extreme rainfall impact. So
Thank you.
yeah, thank you very much.